All right, today we're going to tackle a classic. It's just one problem, but it's a fantastic puzzle from the legendary I.E. Irodov textbook. These are the kinds of problems that really test how you think about physics, not just what you've memorized. So let's jump right in. If you've ever really gotten deep into physics, you've probably heard of this book, Irodov's Problems in General Physics. It's kind of legendary for being, well, tough. The problems aren't about just plugging numbers into a formula. They force you to have a really deep, fundamental understanding of the concepts. And problem 143 is a perfect example of that. So here's the deal. We've got a particle moving in a circle. Sounds simple enough, right? But here's the twist. We're not watching it from the center of the circle. Our viewpoint, our reference point, is a fixed spot on the edge of the circle. And from there, we have to figure out the particle's actual velocity and its total acceleration. And that right there, that's the heart of the puzzle. Changing the reference point changes everything. It throws this whole layer of geometry into the mix that we have to figure out before we can even start talking about the physics. So where do we even begin? Well, with pretty much any physics problem like this, the very first thing you should do is draw a picture. Seriously, a good, clear diagram isn't just a nice to have, it's absolutely crucial. It's the map we're going to use to find our way through the solution. Okay, let's get our coordinates set up. We'll make things easy and put the center of the circle, let's call it C, right at the origin, 0, 0. The problem says we're watching from a fixed point O on the circumference, so let's just place O over on the left side at the coordinate -r, 0. And our particle A is somewhere on that circle moving around. Now for the important part, the angles. See, the particle's true position, the one measured from the center C, is described by this angle, theta. But the information the problem gives us is about the vector r, which goes from our observation point O out to the particle. That vector sweeps out an angle phi at a constant rate omega. So the entire puzzle, the whole thing, comes down to this. We have to find the geometric link between the angle we know, phi, and the angle we actually need, theta. So how do we connect them? It's all about geometry. The coordinates of particle A are just r cosine theta, r sine theta. Simple enough? The vector r starts at O and ends at A. So its components are just the coordinates of A minus the coordinates of O. That gives us r cosine theta plus r for the x component and r sine theta for the y component. Now here's where the magic happens. The tangent of phi is just the y component over the x component. If you plug those in and use a standard trigonometric half-angle identity, the whole messy expression simplifies beautifully to just tan theta half. And boom, there it is, the hidden connection. If tan phi equals tan theta over 2, then theta has to be exactly 2 phi. This is the breakthrough. This is everything. We know phi is just omega times t because it rotates at a constant rate. So that means the particle's actual angle theta is 2 times omega times t. Its true angular velocity around the center is double what we thought it was from our viewpoint on the edge. Okay, now that we've cracked the geometry, we know the particle's true position at any given time. So now we can finally get to the physics. First up, what's its velocity? Let's start by writing down the position vector. We'll call it p, using that kinematic link we just found. It's just r times cosine of 2 omega t in the I direction plus r times sine of 2 omega t in the j direction. And how do we get velocity from position? We just take the derivative with respect to time. Using the chain rule, the 2 omega pops out, and we end up with our final velocity vector right here. Now we've got the vector, but the question asks for the modulus of the velocity. That's just a fancy way of saying its magnitude, or, simply the particle's speed. So to get that, we'll use the good old Pythagorean theorem on its components. The magnitude is the square root of the x component squared plus the y component squared. And what's great is that the sine squared and cosine squared terms add up to 1, leaving us with a really simple speed of just 2 omega r. We plug in the numbers the problem gave us, that's 2 times 0.40 radians per second times 0.5 meters, and we get 0.40 meters per second. And here's the key thing to notice. It's a constant speed. Okay, we've got the velocity. Next up is the second part of the question, acceleration. Now, this is where a lot of people get tripped up. Wait a minute, if we just found out the speed is constant, how can there be any acceleration at all? Good question. Let's find out. To find the acceleration, we just do the same thing again. We take another derivative. We'll differentiate our velocity vector with respect to time. We apply the chain rule one more time, another 2 omega pops out, and that gives us this final expression for the acceleration vector. Now, take a close look at this result. Does that vector part inside the brackets look familiar? It should. It is exactly the same as our original position vector, p. And that little observation lets us rewrite the acceleration in a much cleaner, more insightful way. But first, let's get the magnitude, because the question asks for it. Same process as before, we take the magnitude of that vector. The sine and cosine squared terms once again become 1, leaving us with a constant magnitude of 4 omega squared r. Plugging in our numbers, we get 4 times 0.40 squared times 0.5, which gives us an acceleration of 0.32 meters per second squared. And now for the direction. Since our acceleration vector, a, is just a negative constant times our position vector, p, that tells us everything. It means the acceleration vector is perfectly anti-parallel to the position vector. In other words, while the position vector points from the center out to the particle, the acceleration vector points from the particle straight back to the center, always. So there we have it. We've crunched the numbers, we've got our answers. But what does it all really mean? Let's take a step back from the math and actually interpret the physics of what we just found. Let's just put all the pieces together. We found that the particle is moving at a constant speed. It has an acceleration with a constant magnitude, and that acceleration is always pointed directly toward the center of the circle. Does that sound familiar? It absolutely should. That is the textbook definition of uniform circular motion. And here's how we can do a quick sanity check. We derived our acceleration from scratch, right? But we also know the classic formula for uniform circular motion from our textbooks is a equals v squared over r. So the big question is, do our results match the known formula? Let's find out. We found that our velocity, v, was 2 omega r. Let's square that. We get 4 omega square r squared. Now divide by r, and we get 4 omega squared r. It's a perfect match. This confirms everything. That whole tricky setup in the problem was really just a clever, roundabout way of describing plain old uniform circular motion. So the key insight, the real trick to the whole puzzle, was that geometric relationship we found right at the beginning. The fact that an observer sitting on the edge of the circle sees the particle's vector rotating with an angular speed omega means that the particle itself is actually whipping around the center with a true angular speed of 2 omega. And that brings us all the way back to that fundamental question from earlier. How can you possibly have acceleration if your speed isn't changing? The answer is because your velocity is changing. Velocity is a vector. It has direction. And by moving in a circle, the direction of that velocity is constantly changing, every single instant. And that change in direction, that is acceleration, always pulling toward the center, forcing the particle to stay on its circular path.